Okay, let's get into maintenance here on these belt scrapers. So there's really four really main important steps, and we'll talk about those in depth. But those four steps, you want to clean the blades and the mainframe. You want to replace the blade if needed. You want to check the tension, and you want to retension if needed. So those are our four main maintenance steps. Let's break these down here individually. Let's talk a little bit about tension. There's two types of tension. The first we're going to talk about is what's called radial tension, which is on the right. The second, we'll talk about what we call linear tension, which is shown on your left. Now, radial tension basically rotates the blades into the belt. Radial tension delivers a little bit different force, and it's typically gentler force, and it's typically used on primaries, but it can be used on some secondaries. Now, linear tension is direct force. It doesn't rotate in like radial tension does. It delivers direct force to the belt, to the point where the belt cleaner makes contact with the belt. And there's a couple of advantages of each that I want to talk about here. So rotary tension, it can be detrimental to splices. You've got to be careful when you're using especially mechanical splices and rotary type tensioners. Some rotary tensioners are designed to work specifically well with a mechanical splice. What they typically have in them is some sort of shock ring, a coupler that works to let that mainframe move as that mechanical splice comes through. Some rotary tensioners don't have that, so you've got to kind of know the manufacturer of the rotary tensioner and see how well those tensioners are going to work with a mechanical splice. Rotary tensioners, the advantage of them is they're real easy to install, and they're typically real easy to service. And the reason why they're easier to service is because on linear tension, on tensioning devices that are linear, you have to access both sides of the tensioner. That can be very, very difficult, if not impossible, on some conveyors. If you don't have an access point on each side of the head pulley, it's going to be almost impossible to deliver even tension across a linear type blade. Rotary tensioners can deliver because it rotates that mainframe in, it rotates the entire mainframe in. So rotary tensioners are easier to install, and workers only need to access one side of the head chute to make sure they're checking tension or delivering tension properly. Now, the two photographs that you see on the right are just two different examples of different types of tensioners. The unit on the right, you would put a tool in that, insert a tool in that hole right there and pull down on that tool. With that force being applied, you would set or turn in those set screws. So that's delivering that rotary tension. As that blade wears, you have to come back and retension that thing or check the tension to see if it's tensioned properly. That in some cases can be a two-man job because of the force needed to pull that down and the extra hands that you might need to be using the set screws. The unit on the left, it's a little bit different in that you don't need that tool and you don't have those set screws. This unit has a plunger at the top that you pull up, push the blade up against the belt, push the plunger back down, and then this is actually, I think it's a 3/4 inch nut right here. It might be an inch, that you then apply a couple of clicks through a ratcheting device on the inside of this unit, depending on the width of the belt to deliver that correct pressure. Another type of rotary tension is what we call spring tensioners. And this is a couple of examples of spring tensioners. The unit on the left, you basically measure the compression of the spring to tell you if it's tensioned properly. The unit on the right is very, very similar, except if you look on the back plate of that particular spring tensioner, it's got a gauge that tells you how far to compress down that spring. So this does kind of the same thing. It rotates the mainframe or the blade into the head pulley. There's a nut on that threaded rod. You tighten the nut down, and then you tighten the jam nut down, and that's what keeps your tension applied. And then it needs to be retensioned or inspected as the blade wears. Okay, linear tension, you need some relief for that splice to come through. You don't need those shock rings. You don't need those couplers to allow movement, because on most linear tensioners, the relief is built into the blade. So if you look at the photo on the left, this is a tungsten carbide tipped blade held in place by a piece of urethane. As that linear tension is delivered up, that urethane will flex and give some of that relief that's needed to the splice. So as that splice comes through, in this example, this belt's traveling this way, that splice comes through, because of its angle and because of that urethane having some flex in it, that splice is a lot easier to travel through those points of contact. The photograph on your right, this is not urethane, it's rubber. Same thing, same concept. That rubber will flex a little bit as that clip comes through and make that clip less detrimental to the blades. One of the biggest problems we see with tension is if a little tension is good, you know where I'm going next, hit your raise hand button if you've heard this before. If a little tension is good, a lot of tension is real good. You ever heard that before? So what I hear a lot from maintenance staffs is they get their wrench or they get their tool and they pull down. And if they can't get enough force on it, they get a cheater bar and put that on that wrench or that tool to get more leverage. Belt cleaner manufacturers and tension manufacturers did not design their units to be used with cheater bars. Their intent is to have that tensioner deliver the exact amount of PSI to clean the belt effectively and not cause some other problems. So before it went bust and before it got taken over by the Bureau of Land Management, there was an organization called the U.S. Bureau of Mines. Basically, what the U.S. Bureau of Mines did is they did research. They did a lot of research at their Twin Cities, Minneapolis, St. Paul facility on different aspects of mining. And one of their studies, one of their final studies before they shut the organization down, was to test the tension on belt cleaners. So I want you to look at this graph. The red line is carryback, and moving on this chart from left to right is reflecting an increase in blade to belt pressure. So as we increase blade to belt pressure, our carryback, which is the red line, goes down and eventually flattens out. And that makes a lot of sense. As we tension up belt cleaners, they're going to remove carryback. Now the blue line represents three things that they checked in their study. They checked blade wear from the belt scrapers, they checked damage to the belt from the belt scrapers, and they checked the power requirements that's needed to get past the friction that those belt cleaners created. So again, moving from left to right on this chart, what they found is that as carryback decreases from tension, blade wear, belt damage, and power requirements increase. And at some point in time, blade wear, belt damage, and requirements increase radically. with no impact on the amount of carryback. So when you over tension belt cleaners, you're typically operating right here. And you will effectively remove carryback, but it comes with a price, and it comes to a price of increased blade wear, belt damage, and the power requirements used to get past that drag. What belt scraper manufacturers have done with their tensioning devices is, if belt cleaners are tensioned properly, they're designed to run right here, where you get the full advantage of eliminating carryback effectively without these other parameters being adversely effective. So the messaging on this diagram is simply this: don't let your maintenance staff over tension your belt cleaners. Make sure they're tensioned properly.